start with question 0, and it's going to be the derivation using Nernst's equation of the relation between the potential for the hydrogen couple and the oxygen couple with respect to pH. So the voltage with respect to pH. That is derived on the first principle basis from, well, we'll go back to the second law for free energy in what in my review here. The actual derivation you guys will be doing won't have to go back that far. You'll just take it back to the Nernst equation and use the Nernst equation, and particularly the one that has it in the log form, the log base 10 form, and solve it there. And that's the one I want you to present. So when we get to the point where what you put on paper, I'll mention what goes on the paper, but I want to start with a little further back because it's involving on principles we've been talking about all semester. In fact, this goes back to where we started. And so the first part of it is, this is for non-standard conditions. And so non-standard conditions, we know that delta G has various ways of being, various representations, but the one that's most convenient for this particular problem is the expression that expressing delta G in terms of the free energy under standard conditions plus this term, which takes into account the reaction quotient. And this one is the one that we use as our basis. And so then all we have to do is fall back on the fundamental definitions, because what is the Gibbs free energy? What does it represent physically?
The amount of energy to all vibrational degree of freedom.
Well, more importantly, it is a maximum something. Yeah, it's the maximum work available in any particular system. And so we start with the Gibbs free energy. That definition now, how do I relate that to what type of work are we talking about with this? Electronic work. And so I can use the definition that delta G is equal to minus N, I'll put a little subscript E, for the number of moles of electrons times a Faraday times the potential. And then I can make that substitution in here. With respect to the standard potential, the potential that gets measured under standard conditions. And that, and I'll leave this term alone. Okay. So now all we need to do is divide both sides by the number of moles in the Faraday. And that gives us the Nernst equation. But this isn't the one we're going to be using. We're going to be using the Nernst equation, but this particular form is useful as a starting point. But since we're going to be working with the function in terms of the pH, which is the log base 10, the negative log base 10 of the hydrogen ion concentration, this form is not going to be as convenient. So what we would want to do, how would I convert natural log to log? Yeah, there's a simple multiplicative factor. I just add that in. So now I'll re-express it again. So E is equal to E naught minus 2.303 RT over again F times the log. This would be much more as greater utility. And since the non-standard conditions we're going to be discussing are not going to be, we're not as interested in the temperature features, we're going to be interested in the change from what conditions. What's going to change? We're not really interested in the temperature at this point. What are standard conditions?
25 degrees.
25 degrees Celsius and 1 atmosphere for every gaseous reagent and 1 molar concentration. So we're really interested in how the potential changes with respect to concentration. After all, we're interested in how it functions as a concentration of the hydronium ion in solution. So we're following it in terms of the pH. Hence, we've got it in the log form, which is has greater utility. And since we're going to be at 25 degrees, and so at 25 degrees Celsius, 2.303 RT over Faraday. And this is R, which R are we using? Which R would it be?
8.31.
Yeah, 8.314 joules per mole K, and the Faraday is in coulombs per mole. That's the amount of, what is the Faraday equal to anyway?
Well,
It's the, what is a Faraday?
it's a charge per area of capacitors
Well, it's the charge on
on a surface.
Of a certain amount of
Particles.
the electrons. Yeah.
Well, it's any, I thought it was any charge.
Well, well, because the charges come in elementary units, but it is. Yeah, it's not necessarily restricted to electrons, but we are interested in electrons, and so it's going to be the charge on a mole of electrons. So if Faraday's 96,485 coulombs per mole, which we'll be using later on when we deal with Faraday's law. So that turns out to be equal to 0.0592 joules per coulomb. Okay? And what is a joule per coulomb? A volt. Yeah. A volt is the measure of how much work is done for every coulomb of charge that moves across a charge difference. And so that means that this is equal to 0.0592 volts. And now I can substitute that in our expression. And this is the expression you're going to use as a starting point. So I want you to be able to, rather than memorize the equation, although this one's pretty easy to memorize, and you probably will have it memorized after you've done it a few times. Practice this. Practice it starting from the free energy expression, and then just substitute in what these represent, because take into account free energy is the maximum work. This is the maximum electronic work. And then you substitute that into the equation, and then we want to cast it in a form that's going to be usable in our particular application. So this, we're going to end up, and this is the form we want. So it's going to be E is equal to, or epsilon, minus 0.0592 volts over N. Times the log. And that's what you're going to use as a starting point for the derivation. So you'll start with this. And you could, the test is Tuesday, so I can just memorize this equation. But that wouldn't be as effective.
So what do we have to know about Faraday's number?
96,485 coulombs. Perhaps would be a good idea. You'll need to know this number, or you can calculate it yourself. I might provide it on the test. It might be buried somewhere else on another question. But it wouldn't be a bad idea to know that. what a Faraday is. Although, in this case, it drops out, we dropped it out right over here. And so, you definitely need to know this. But I want you to be able to understand this because this goes to what we're doing all semester. Go back, we started with thermodynamics.
So R is going to be 8.314.
Yeah,
What are the
8.314
units
joules.
on that?
Joules per mole per Kelvin.
And it's going to be at 299 Kelvin or 298.
Yeah, 298, or, yeah, 25 degrees Celsius, 298 Kelvin.
What was Faraday's?
96,000 Faraday. There's 96,485 coulombs for every mole of electrons. I'm going to probably, when we go to Faraday's law, I'll use a formula, I'll provide it for you. The simplification, we'll round this off to 96,500 coulombs per mole.
So you're gonna provide.
But I'll provide it.
Oh, it's just joules. Okay.
I'll provide a Faraday. Okay, so let's solve that problem right now. I'll let you know this, and when the application's going to be clearer, we'll use a simplified version, 96,500 coulombs. It's just going to be more convenient for the purpose of calculation. Okay, but the bottom line is, when you start your work, this is what you'll start with. But as always, rather than memorizing the 300 billion possible equations, you want to know and memorize a few laws. And the laws, when the laws are cast in a mathematical form, that enables you the greatest flexibility. So you take the mathematical expression corresponding to a law and then fashion it into the appropriate form for the problem at hand. That way you're not memorizing a bunch of equations which you'll forget a day after the test or a couple days after the test. You keep reinforcing the law and apply the law, because that's really what we're here for, is how to apply the law to a given set of conditions. And so the question I'm going to ask is, derive the expression for the potential as a function of pH for the hydrogen couple or the oxygen couple. It'll be one or the other. I'm going to be both right now. Okay? This is our starting point. Okay, so having said that, now I'm going to erase all of this and start.